Okay, so all of you bums at home are good to go. You can see that, right? Max, Gesundheit. I just happened to look when you were sneezing.
Thank you.
That was a little weird, I know, I'm sorry. Okay. You kids ready to go? Yeah. You kids ready to go? Yeah? Okay, so before we get started, if you go into Schoolology again, in the Chapter 2 folder, you will find a document called, hold on, that's not what it's called. It's called, come on, Rita, you're better than this. It is called Chapter 2. Yeah, related rates examples. If you are working on your iPad, even if you're not working on your iPad, you might want to fire that up because that will save you a lot of hassles of having to write down these lengthy word problems. Okay. All right, good. I almost forgot that. Okay, so what are we doing today? We are talking about related rates. These are also known as word problems. They're awesome. They're awesome because they allow us to take all this calculus garbage we've done so far and relate it to somewhat real-world examples. Okay? And it requires a little bit of understanding of what we're going to be doing. So, for instance, we're going to find a related rate. We're going to use a 9-step approach. So I've come up with a 9-step approach that I think works really well. And we're going to use that 9-step approach to start these problems. And as time goes on and you get better at this, you'll probably be able to chop out all 9 steps and get it down to 5 or 6. But each one of those has an integral part in trying to solve these problems. There's a reason why we finished Chapter 2 up to this point, took a test, and are doing this. Related rates is a topic that comes up on every single AP test I've ever seen them give. Okay? And they're usually fairly involved problems. So, in other words, it's a very important topic that we're going to spend some time going over. And then, of course, you should enjoy spicy foods. Yep, right? Spicy food fan? Yeah? Good? Good. Okay. So, we did implicit differentiation. We used the chain rule. And when we did the implicit differentiation, we were taking a derivative, that dy over dx notation that we used. Okay, that meant take the derivative of y with respect to x. Okay, meaning x was our variable. What's going to change here is our variable is going to change to time. And so it's going to allow us to model a whole bunch of problems involving time. Unfortunately, a lot of these things are involving negativity, like falling and dropping and running into things and colliding and accidents and all that kind of stuff, but we'll work through that over time. Okay, so we'll start with this, which isn't a very fun problem because it doesn't really have any ties to the real world. It doesn't involve 2 boats crashing or you falling off a ladder. It's just a straightforward problem here. Okay? You'll recall when we did this is related rates. When we did implicit differentiation, the x stuff was okay. Whenever we took a derivative with respect to x, it was just the derivative. But whenever we took the derivative with respect to y, we had to include a y prime on there. Because t is our variable now, anytime we take a derivative, you have to include a dy dt or a dx dt. Okay? So, here's the problem. We've got this function y equals x squared plus 3. Find dy dt when x equals 1, given that dx dt equals 2 when x equals 1. Okay, well, what does that mean? Well, I got to do a bunch of derivatives. Okay, so we start by taking the derivative of both sides. And you'll notice a change in the notation. We're taking a derivative with respect to t, not with respect to x. So y prime we can't use y prime anymore. It's got to be this d over dt. Okay. The derivative of y would be 1, dy dt. The derivative of x squared plus 3 would be 2x, dx dt. So you stick that dx dt or that dy dt on the end of each one of those. Okay? Now, in this derivative, I should say in this equation, how many unknowns are there? 3. Good. dy dt, x, and dx dt. If we go back to the problem, we know x, we know dx dt, and we're looking for dy dt. If you've done it correctly, you should have one less chunk of information than the number of unknowns. I don't know if that statement made any sense. If there's 5 unknowns in the problem, you better know 4 of the 5 unknowns, otherwise you can't solve it. Okay. So we plug and chug there. We put in 1 for x, we put in 2 for dx dt, and dy dt turns out to be 4. Okay, problems? Problems. Problems? Problems? No problems. We're good? Okay, not very fun. Boring. That, by the way, is called a naked problem. It's called a naked problem because it is not tied to anything that we're going to do in the real world. We won't do a lot of naked problems because there's no fun in them. We want to look at all kinds of real world situations. Okay. So pretty much the rest of today is going to be just that, real world situations. We'll put it in quotes. Okay? And like I said, this is some of the stuff we're going to do. Calculating how long it takes to empty a pool. Calculating when will 2 cars crash into each other. Calculating how fast you're traveling when you fall off a ladder. All of those funny things. Okay? So, here we go. Here's the 9 steps. And again, when I start solving these problems, I'm going to follow all 9 steps. In a day or two, you won't need all 9 steps. But initially, this is going to be crucial. Number 1 is draw a picture. Okay? If you're talking about a ladder against a wall, then draw a picture of a ladder against a wall. If you're talking about 2 automobiles crashing, draw a picture of the 2 automobiles crashing. Number 2, define the variables. Okay? So, if you have, for instance, you're up on a ladder and the ladder starts to fall, well, are you representing the length of the ladder as d? Are you representing the length of the ladder as L? Are you doing the vertical height as X or Y? Just because everybody can label it differently, and therefore you want to define your variables so that when somebody sits down to read this problem, they know that you're defining the distance that car A traveled as A or Q or whatever it is you're dealing with. Number 3, what do you know and what are you looking for? Okay? In other words, what's your given information and what am I eventually going to solve for? Okay? I know how long the ladder is. I know how fast the bottom of the ladder is sliding out. How fast am I falling down? Number 4, write a general equation. You will see as we work through these examples that the same types of problems continue to pop up. Do not plug any given information into the problem yet. That's going to be a tendency that you're going to have to break, is that you're going to want to put in stuff you know right away. Don't do that. Unless it's a value in the problem that never changes, you don't sub anything in yet. Number 5, take the derivative. The nice thing about step number 5 is in related rates problems, the derivatives are usually not that difficult. So that's not the difficulty there. The difficulty is the other 8 steps. Number 6, snapshot. Okay. That doesn't make much sense right now. Just write it down. I'll explain it to you later. The snapshot is that one instance in time we're going to be looking at. Number 7, solve it. Okay, so you have a derivative, you know some information, you're going to plug it in, you're going to solve. Okay. If you prefer, plug and chug. Number 8, does your answer make sense? Okay, this one's a little tricky. So for instance, if you're solving a problem with, let's say, dropping something out of an airplane, and you get an answer. And let's suppose that answer is something like 4 years. You probably did something wrong. Okay. Or you calculate the velocity of a car, and you get something like 1,400 miles per hour. Okay, that's probably a little fast. So There's going to be other instances where you're going to get done with the problem and you're not going to have any idea whether or not it makes sense. But just stop for a second and say, is it reasonable? It is not reasonable for a car to travel 2 times the speed of light, okay? Or 2 times the speed of sound, or, there will be some ridiculousness that pops up. And then number 9, don't forget units. It's a word problem. You got to include your units there. Are we talking about feet per second? Are we talking about the number of rabbits? Are we talking about miles per hour, et cetera, et cetera? All right, you ready? You guys ready? Yeah. Good. This is what my life is like. You're talking to screens that no one ever responds to. Occasionally you'll get one of these, or but the effort of reaching forward and hitting the unmute button the struggle is real. We're in class making fun of all of you. I hope you don't mind. All right, we're going to blow up a balloon. Okay? So I'm going to click through this, and this is going to be a very slow process, a very methodical process. But what I have found is if I go slower, things will make more sense for you. And some of you might be bored by this. Some of you might be like, "Get a move on it," but I don't care. I'm going to go slow. Okay. So air is being pumped into a spherical balloon at a rate of 4 cubic feet per minute. Find the rate of change. We've heard that phrase before. Of the radius when the radius is 2 feet. Okay? And then there's a picture. All right, so I started by drawing a picture. It's not a great picture of a sphere. Give me a break, will you? It's a circle with a radius of r, which is actually a sphere, but who cares? Number 2, define the variables. Don't assume that the person reading your problem knows that r is the radius and v is the volume. Write it down for them. Number 3, what do we know and what are we looking for? This is going to be the biggest struggle. Step 3, I think, is going to cause the most problems for you. So you have to take the wording that I had in the original problem and relate it to calculus. In other words, you need to be able to pull that 4.5 out of there and realize that that's a change in volume. It's the rate of change of the volume. Cubic feet per minute is a rate. Okay, so I wrote that as dV dt. The change in volume with respect to time is 4.5. And it's positive because it's getting bigger. We'll run into some problems where that rate will be negative because it's getting smaller. I'm looking for the rate of change of the radius, dr dt. And when do I want to know dr dt is when r is equal to 2. This is going to be the biggest challenge and also the most important part of the problem. What am I looking for and when am I looking for it? Or what am I looking for when what occurs? What are we on? 4? Okay. We good so far? Number 4, write a general equation. All right. Any ideas on what I'm going to use for a general equation here? Anybody? Bueller? What are we dealing with?
Pi r squared.
Say again? Say
I
again.
said like pi r squared, or like a circle equation.
Close. It's deceiving because my picture is a circle, but we're actually dealing with a sphere. So how would you change your answer, Prasant? No idea?
Is it like, I know it's like pi r cubed, but I forgot like the variable in front, or like the number in front.
Yeah, and
For like the,
yeah, and I don't expect you to remember the formula, but we're dealing with the volume of a sphere, yes?
Yeah.
Yeah. Okay, volume of a sphere. Now, the nice thing about this is that you won't need to memorize the old geometry formulas that you had. Anytime, I shouldn't say anytime, most of the time, when you have a three-dimensional figure, they will give you the formula that you need. So you don't need to remember the volume of a cylinder, pi r squared times h. You don't need to remember the volume of a pyramid, for instance. What do you need to know? You need to know the area of a circle, you need to know the area of a square, you need to know the area of a rectangle. Basic formulas. Volume formulas, they'll usually give you. Okay, step 5. Take the derivative. Okay, go ahead. You take a derivative while I go get a drink.
My brother, he's like, God damn, I can't even sleep to that class now. It's an idiot.
Good. Amanda, did you notice anything interesting about the derivative of the volume of a sphere?
It's 4 times the area of the circle.
Yes, which is also what? Does that? I know you had a really good geometry teacher, so you probably remember. Well, first of all, what did you get for an answer?
4 pi r squared.
Good. You don't remember what that is?
No.
That's actually the surface area of a sphere.
Okay.
Okay, now, your answer is almost correct because remember we're doing related rates now, so our variable is time. So you would actually get that. Okay, the derivative of the volume is dv dt. The derivative of v is 1, dv dt. The derivative of the function is exactly what she said, 4 pi r squared. But since we took a derivative of r with respect to t, we need a dr dt on the end of it. Yeah, and that's one of those weird things that the derivative of a volume of a sphere is the surface area of a sphere. All right, how many unknowns in that problem?
2.
3, right. 3 unknowns, dv dt, the rate of change of the volume, the radius, and dr dt, the rate of change of the radius. Remember, pi is not a variable. So if you go back to step 3, where we listed what we know and what we're looking for, we do know 2 of those 3 things. We know dv dt, and we know r. So step 6 is a snapshot. Now, what I mean by snapshot, aside from plugging and chugging, is we're plugging stuff in at that exact moment in time. And what is that exact moment in time? That exact moment in time is when r equals 2. And that's why in step 3 we said when r equals 2. We're looking for dr dt when r equals 2. We get that. Which is good, because there's only one variable left, and I can solve for one variable. You pick up your handy-dandy calculators. I would do that instead of trying to solve that. 4.5 divided by parentheses, 4 times pi times 4. Or if you're feeling saucy, 16 pi, close parentheses. Make sure you put it in parentheses. Okay. Not 4.5 divided by 16 pi, because it will give you a wonky answer. Let's review that. Those 2 phrases seem to be the same thing. However, if you type them into your calculator, you get different answers. Okay? Why do you get different answers? Because the calculator knows your Aunt Sally. This first case, the calculator is going to say, okay, take 4.5 and divide it by the product of 16 times pi. In this second one, the calculator says, okay, take 4.5, divide it by 16, then multiply it by pi. This is no good. This is good. And since it's a word problem, most of the time in a word problem, we're going to want a decimal answer here. And so we would get 0.09. Now, I know I said earlier 3 decimal places, but if you look at the number on your calculator, it would actually be 0.090, so we can just do 0.09. As we solve related rates problems, a big struggle becomes units. So I'm going to show you a trick on how to solve for units here. Some of you might already know what the units are, but I would tell you that that can help you determine the units. Because we solve for dr/dt, to get the units, you just ask yourself, well, what units is the radius in? And I don't remember. Was it feet?
I think so.
We'll go with it. Over the units of the time. Minutes? Minutes? Minutes. Okay, done. The units of the left-hand side of this equation have to match the units to your answer. Let's see if I click. Oh, we're going to get to that in part 9, so I jumped the gun a little bit. Sorry. Does your answer make sense? I have no idea if that answer makes sense. I don't know how fast a balloon fills. So step 8 kind of is a waste of time in this particular case. And you'll find that in a lot of the problems is that you're not, I don't know. I never measured inflating a balloon. And then step 9, the units. All right, let's stop for a second. Questions on the process? We're good? How bad does it seem on a scale of 1 to 5? Give me the number of fingers. Careful which one you give me. 5 is being really difficult. Oh, wait, what are we doing? 1 is easy, 5 is difficult?
Yeah.
Okay, 1 is easy, 5 is difficult. How bad does this seem on a scale of 1 to 5? 4s? Okay. All right, good. I forgot what I said. Was 1 easy or hard?
One was easy.
All right. All right, let's do one more, then we'll take a break for a little bit, then we'll come back, and we're just going to keep going through the slideshow to get all these problems done, because what we're going to see is changes in the types of problems. Okay, this first one is a geometric-based problem. It's based on some type of geometric figure, in this case a sphere. We'll see cylinders, we'll see pyramids, we'll see weird-shaped trapezoidal prisms in a swimming pool, but for now we took something simple like a sphere. Okay, now let's make it a little bit more interesting, and we're going to take, this is commonly called a leaky bucket problem. It's just a general term for problems involving filling or draining containers. Okay? So in this case, we're going to drain a cone, a conical tank. And like I said, there's the volume of a cone. And there is some logic here that the cone would be upside down, like an ice cream cone. Okay, you're not going to fill a conical tank with it being like what you would imagine a cone being. So, there's the problem. And this one introduces a whole bunch of different types of things that we need to be concerned about. We're going to come back to this in a little bit. Okay, because we're not going to work with gallons, we're going to work with cubic feet. Okay. I'm assuming you can read. Notice it's an inverted right cylinder or circular cone. It has a height of 12 and a base of 6. So that's the shape of the figure that we're dealing with. And then we're going to start putting some stuff in there. I don't remember. Give me a second here. Okay, so there's my picture. At any given point in time, the water in that tank has a radius of r and a height of h, as opposed to the tank itself, which will always have a height of 12 and always have a radius of 6. What do I know? Whoops, sorry. Number 2. define your variables, the radius and the height. I also forgot the volume. So V would be volume. V equals volume. There we go. There's step 3. What do I know? What am I solving for? So this 10 gallons per minute is my change in volume. And then you'll notice I made a little conversion here. Since everything else in the problem is measured in feet, I need to have my volume in terms of feet also. So I used a little Gazinta bar work there. Or from chemistry, it would be factor label method to convert that. This is not something you'll need to memorize. They will give you that conversion because it does pop up. We'll solve problems where we're pumping rocket fuel. We'll solve problems where we're pumping oil or some mysterious fluid. But they will give you that density conversion thing. I'm looking for dH dt when h is equal to 3. Okay? Questions so far? I know you're writing like mad, people, but eventually you'll need some time to process this. So let me know if I'm going too fast. Am I going too fast? Good, good, okay. Boom. This one's weird because there's 2 different approaches to it. I'll take you through both because I think it's important that you see both of them. There's my general equation. What are we on? 5? 4? 4? 5?
Four.
General equation 4. Step 4. There's the general equation. I gave that to you. Step 5. Help me out, Paige. What's 5?
It's the take the derivative.
Take the derivative. Okay. So take the derivative of that puppy. Remember, anytime you take the derivative of a variable, you have to include the variable. So if I'm taking the derivative of v, I need a dv dt. If I take the derivative of an r, I need a dr dt. You'll notice in this problem, though, I've got an issue because I have both r's and h's. When I was dealing with the sphere, all I had was an r, and I was good to go. Now, all of a sudden, I've got this puppy. Okay? So the 2 approaches go like this. I can do some math and get rid of one of the variables, my preferred method, or I can just grind it out and get rid of it later. I prefer the former, not the latter. Okay? So to do that, you'll recall from geometry, we did a little similar triangle thing. Okay. So again, let me review here. There's too many variables in that problem. If I had to take the derivative of that, I'd have to do a product rule with these 2 guys. I'd have a dr dt, a dh dt, a dv dt, r's, h's, and v's flying all over the place, and it's a mess. However, if I get sneaky and use a little bit of geometry, I can get rid of one of the variables. And you remember this from geometry. Similar triangles would give us this. So I would set up this equation. The radius of the big triangle over the height of the big triangle is equal to the radius of the water over the height of the water. Cross multiply and get to that. And before I just blindly move on to this next step, I need to think to myself, because I did this already because I solved the problem, I think to myself, well, what variable do I want to get rid of? I could get rid of the h, or I could get rid of the r, and I have to make a decision. And what's that decision based on? If I go back a couple slides and look at what I know, everything that I know and am working for is in terms of h. There's no r information in there. Therefore, that's why I want to get rid of r. Okay, so I solve this equation for r to get this puppy. Then I take this mess and plug it in there. When I do that, now I have a prettier equation that's just in terms of v and just in terms of h. Give me a thumbs up if I'm if this pace is okay. Don't give me a thumbs up if I'm going too fast. Okay. All right, good. All right, so I'm doing a little bit of work on the front end before I get into the calculus because it will make my life a lot easier. Why is that thing still there? Go away. There we go. Okay, so I would get that. I subbed in for R, and I get that monster. I'm not going to take a derivative yet because I still want to clean that up to get to that. And remember when I was giving you the 9 steps, I said, oh yeah, the derivative in most of these problems is really easy. Yeah, I think that's a pretty easy derivative. Okay, so do that. Take the derivative. And we'll see how you do with the little idiosyncrasies. Is that right? Idiosyncrasies? Okay, we're going to go with it. All right, Bella, what do you got for me? You're on the spot.
Okay, so I said dv over dt equals pi fourth h squared and then dh dt over
Wonderful.
dt.
Wonderful. Perfect. Okay. Any questions on her derivative, which is the same that I have? Good. Requires no discussion then. How many unknowns? There are 3 unknowns. dv dt, dh dt, and h. We know 2 of those unknowns. I forget what step we're in. I think it's 7. Solve?
Yeah.
We're going to go with it. 7. Solve. Okay, so plug and chug. Pick up your handy dandy calculator and solve. We get that. Does the answer make sense? I have no idea. It seems reasonable. I mean, going up 1/10 of a foot per minute? Okay, sure. More importantly, what I would look at is, in the terms of does it make sense, is the sign on the answer. The tank is being filled, therefore the height should be going up. If the tank is draining and you have the height going up, there's something wrong there. And then, of course, I included the units. Where'd the units come from? Well, dh dt, the change in height, which was in feet, and versus the change in time, which is minutes. Okay? All right, let's look at the other method, which you're probably not going to do, but I'll show you anyways, just so I can say I showed it to you. All right, this is the derivative of the first equation without doing the similar triangle stuff. This stuff in the middle is the power rule. Or sorry, the power rule. Come on, Reedy. The product rule. And I've got some issues in there. I've got some issues because I don't know anything about R. I don't know anything about dr dt. So I have to figure out a way to get rid of them. So that's just cleaning it up a little bit. And as I said, we got to figure out a way to deal with the R and the dr dt. It still involves a similar triangle because we have to, that's the equation I got when I set up the similar triangles and cross multiplied. When I take the derivative of that, I get to this. And this thing all of a sudden introduces a dr dt, which is good. So now I know what dr dt is. What about R? Well, I get R from the original slide, or the original equation. So I know that the volume is 1/3 pi r squared. I know what h is. I know what the volume is. I plug and chug to find R. This to me just doesn't work in my melon. I don't like taking this big scary derivative involving a product rule. I don't like having to go and still set up the similar triangle equation and then take the derivative of that just to get rid of dr dt. I don't like going back to the original problem. But it is another approach to solve that type of problem. I think you all agree that my first method is a little bit better, yes? Okay, good. So we won't beat a dead horse here, we'll just move on. All right. I have 10:40, let's take a 5-minute break, and then we'll take a look at some ships. Okay? Beautiful. For you guys, get up, stretch your legs, go for a lap, use the bathroom, get a drink, take a nap, whatever. Take a lap, don't cause a ruckus.
Okay.
You know.
Those first two problems. Oh, I got the two, I think are both E. Yeah, we both did E, and B and C. We do A. And like 9 and 10, I thought we did right.
I'm taking my oceans test and going there. Okay, that'd be fun. Can I come from like the auto shop? What do you do for lunch? I did lunch tonight. I had B lunch for a day. I'm gonna sit out.
Paige, is your sister in the same group as you?
Yeah, she doesn't have to get here until like 12:30. She has lunch and then she has dance and she doesn't even have to come in for
You
dance.
stinking freshman.
I was like, Russ, that's not fair. She'll be here tomorrow though. Yeah, tomorrow I get.
How many do you have today?
I have 4.
4, 4, 3. Yanni, how many classes today?
5.
5? How's that possible?
I have 0 hour.
Oh
What do you have 0 hour?
Weights.
But you're not doing that here.
No.
Okay,
Wait,
so,
how many classes do you have tomorrow then?
2.
Okay.
but wait, how does that work then? Do you lift at home?
Yeah.
So you, all right, I'm processing. So you lift at home 0 hour.
Well, like on days where at school, it's a little different because like if I have to end a little earlier to get to school on time.
Okay.
But like if we're online all day, then it's not really a problem.
And so you get here for, you have weights on A and B day, or
No,
just
A.
just A? So today, oh boy. And which lunch do you have? First or second?
Today I have second, I think, and then tomorrow I have A lunch.
Yeah, how does that work?
Some classes, so both of, I have a first and second period. So both of those classes, I'm lucky enough to have B lunch, which means they come to class
It's
first.
just the same as at home. So
Yeah.
did some classes have to change then?
Yeah, like Kanupke has A lunch on one day and B lunch on another day.
Oh.
Yeah.
I have B lunch both days.
It's the way to go.
Yeah.
Yeah. So like today, I have, you guys 6th period, I teach next hour, and then I have the rest of the day off.
Oh my God.
Except for 4th period, I have tutoring, so I sit on Zoom and wait for people to come in and ask questions. Okay, everybody back? We're good? Let's rock. We only have a couple minutes left. hopefully we can get through this problem. Before I get into this problem, though, let me talk a little bit about this. This stuff is difficult. Some of you might be sitting there thinking to yourself, I'll never be able to do this by myself. You will, it's just going to take some practice. So what it's going to look like is, unlike other homework days, when you come back tomorrow, I'm not going to work any problems from start to finish. What I'm going to do is give you some nuggets of information and then let you go back and work on them. So this homework tonight is not due tomorrow, because you're going to need some time to get in there and get your hands dirty. You need to try these problems. You are not going to learn this stuff by just copying answers off the answer key. Okay? So again, get in, try the problems, get frustrated, because you will. Cry a little bit if you'd like. I know, Max, you're probably going to have a little bit of crying there going, but it's okay. We still love you. And then when you come back on Friday, we'll talk about some of the problems. I'll help you set some of them up. I'll give you some hints, push you in the right direction, and then continue going. We're not going to finish the slideshow today, so the first thing we'll do on Friday is pick up where we left off. Okay? So, second type of problem. We got some ships. And I'm assuming that you all know the difference between north, south, east, and west. Okay, never eat soggy waffles. And at 1 o'clock, ship A is 25 miles due south of ship B. Okay, so ship A is starting, you can't see at home, sorry. Ship A is starting here. And then it starts sailing west. So I chose to call that direction X. Makes sense, it's horizontal. While that's going on, ship B starts up here and starts sailing south to where A used to be. Okay, so the ships are doing this. And as they move, they have some distance between them that is going to change over time. It'll get bigger, it'll get smaller, who knows? That's what we're going to calculate. So there's a whole bunch of chunks of information in here. For instance, 20 miles per hour for B, 16 miles per hour for A, and then some time that we need to work out here. So here's my starting picture, and you can label this a couple different ways. I chose to do it this way. I called the distance that ship A has traveled as X, and I called the distance that ship B has traveled Y. Therefore, this distance, this is kind of an important concept there, that distance from B to where A started is going to be 25 minus Y. Okay. So what I'm looking at in this picture is a snapshot at some point in time of where A and B are. Okay. So number one, picture, got it. Number two, whoa, hold on. Number two, variables. So X is the distance A for ship A, and Y is the distance for ship B. Z is the distance between the ships. Okay. Step 3. What do I know? What am I looking for, right?
Yes.
Okay, I know that dAdt is 16 mph. I know that dBdt is 20 mph. And I'm looking for the rate at which the distance between the ships is changing at 1:30. Okay, I'm looking for dz dt when t equals 1/2. Is everybody good with the 1/2? I'm going to keep everything in terms of hours, so 1:30 is 1/2 hour after we started. Okay? Step 4. I don't remember. What's step 4? General equation?
Yeah.
General equation. Okay. This is what we commonly call a Pythagorean theorem problem because we're going to use Pythagorean theorem. So my general equation, if I look at the picture, would be x squared plus 25 minus y quantity squared equals z squared. No sneaky stuff to do here. I don't need to replace any variables. I'm just going to go. I believe step 5 is derivative, right? Okay, derivative. Now, how do you want to take the derivative? We've talked about this already. Do you want to multiply out that binomial? Do you want to use chain rule? I'm fairly bright. I'm going to use chain rule. 2x dx dt. I took a derivative with respect to time for x plus 2 times the quantity, 25 minus y, times negative 1 times dy dt. Okay, bring the 2 down, reduce it by 1, chain on the derivative of the stuff inside. Derivative of negative y is negative 1. 2z dz dt.
Wait, I have a question.
Certainly.
So you said dA dt and then dB dt, but then on the bottom we went to dx.
Oh, good point. Glad you're here, Paige.
I was just like,
No, you're right. There we go, that's better. Good catch. Okay, again, I'm going to make my life a little bit easier. Get rid of the 2's. You don't have to. You can work with the 2's in there. It's okay. All right, so I know what dx dt is. It's right here. I know what dy dt is. It's right here. I'm looking for dz dt. But now I have a big problem. I have no idea what x, y, and z are. So we do what I call a sidebar. I come over here into this space and I do some other calculations to figure out what x, y, and z are. So if A started here and travels that way at, what's A? 16 miles per hour for a half hour, how big is x?
8.
It's the dirt equation, right? 16 miles per hour for 1/2 hour gives me a distance of 8. Similar calculation for y. 20 miles per hour for a half hour makes y equal to 10. Now z. Well, where do I get z? If I go back to my original equation, I can solve for z there. So 8 squared plus 25 minus 10 quantity squared equals z squared. Oops, z squared. Let's see, 8 squared, 64, 15 squared, 225 plus 64, 225, 289, and that's a perfect square, so I think z... Don't try this at home, kids. I think it's 17.
Yeah, that was it.
Yeah, did that in my head. Or I cheated. You'll never know. Now I know what x is. Now I know what y is. Now I know what z is, and therefore we can plug and chug. Running out of room, but I think I can squeeze it in there. 8, well, that's an 8. 8 times 16 plus 25 minus 10 times negative 1 times 20 equals 17 times dz dt. All right, bust out those crazy calculators and tell me what the answer is. We're running out of space, so I'm going to come over here and say that dz dt is equal to
I got -10.5
Negative 10.118. Can somebody confirm or deny Paige's answer? And I mentioned her name so we can blame her if she's wrong.
I got that.
You got it?
I got that.
We got one confirmation. Uh-oh. Kaylee, was that a confirmation?
Yeah.
Beautiful.
Yeah,
We're gonna
that's
go.
fair.
We're gonna go with it. Fine. Okay. Okay. Hold on. Let's finish this, and I'll ask my questions. What are my units, Paige?
Is it miles per hour?
Yeah. Don't overthink it. It's miles per hour. Okay. Is anybody bothered by the negative number?
Yeah.
Okay. What does the negative number mean? Little physics interpretation there. Say again.
You're traveling opposite?
I mean, because if you go this way, that's positive, and if you go this way, it's negative.
Okay, so think of it this way. If the two ships were heading towards each other, the distance between them would be getting smaller. That's fairly obvious. If the ships were going apart, the distance between them would be getting bigger. That's fairly obvious. Now all of a sudden I've changed the rules. I've done this. What this negative number means, I can't write on the board anymore, is that the distance between the two ships is getting smaller at that point in time. So the negative number in this problem is okay. It just means that the quantity, z, is getting smaller over time because it's a rate of change. The rate of change being negative means it's getting smaller. Okay? Whose head's ready to explode? Awesome, thank you.